Symmetrical inversion around a fixed point, especially in regards to posttonal music, is a vital process both in composition and analysis. Symmetrical inversion of a pitch set reverses the direction of the distance between each element relative to the first element. Mathematically, the process of determining the inversion of a set is as follows. Given a set xy, the inversion of the set would be x. The distance between y and x, y minus x, reversed, negative sign, and then added to x. For instance, if the initial interval went up by a minor third, 0, 3, then the inverted set would go down by a minor third, 0, negative 3, while the first pitch of the set remains the same. To visualize this space, we start with our simplest cases in order to determine the boundary of I space. Points that will invert onto themselves, for instance 2, 2, are of the form xy, where x equals y, similar to P space. Therefore, the boundary of I space is also the line y equals x. Now let us consider a point not on the line, say 3, 1. From the first element to the second element, we went down 2 semitones. The inverted set must go up 2 semitones from 3, 3, 5. Each point below the y-axis will be mapped onto a point equidistant above the x-axis, which still maintains the x value. Since every point below the line y equals x is mapped above it, we can again represent the space using the inequality y is greater than or equal to x. However, simply because P space and I space in two dimensions can be represented by the same expression does not mean that they are the same. The processes by which they are attained are obviously different, and as we apply other equivalencies or move into higher dimensions, they will no longer coincide. Let us consider the model for OI space. Because we are now in mod 12, negative numbers no longer exist. So the set 0, 4 would have mapped to 0, negative 4, but now maps to 0, 8 under mod 12. Therefore, any interval that inverts onto itself implies that the set containing that interval will also map onto itself, namely the interval of a tritone. Given the set 1, 7, the inversion of that set would be 1, negative 5, which is now 1, 7 in OI space. This is true for any transposition of this set, meaning the line of transposition of the set 0, 6 is also a boundary in OI space because we're in mod 12. Remember that mod 12 maps 6, 12 to 6, 0, so the line will continue up from the bottom of the 12 by 12 plane when it passes x equals 6. Now, as we did with OP space, we will look at OI space in three different ways. First, we will apply I equivalents to the 12 by 12 plane of O space that has not been folded. On this grid are the points 1, 10, 4, 1, 8, 6, and 11, 9. We now apply I equivalents resulting in points 1, 4, 4, 7, 8, 10, and 11, 1. We then fold this space into a torus. Directly opposite from the line y equals x is the other boundary. This space can be described as a torus that has been cut by a Mobius strip. In our next model, we will fold the plane into a cylinder before applying I equivalents, and then continue by folding it into a torus. And finally, we will start with our complete torus, and then apply I equivalents. Moving to OTI space, we will start with OI space with lines of transposition marked on it. The boundaries of OI space y equals x and the transposition of the set 0, 6 will be maintained as boundaries in our resulting space. This maps onto a semicircle where the points equal directionless intervals.